Okay, we're going to look at normal renal physiology, and then we're going to look at acute kidney injury and then also acute tubular necrosis. But I just want to go back and review your normal renal physiology. So what we have here is we have the nephron, and so you've got the afferent arteriole, the glomerulus, the efferent arteriole, the peritubular capillaries. You've got the Bowman's capsule, the proximal convoluted tubule, loop of Henle, distal convoluted tubule, cortical collecting duct, and then principal cells. Now, the distal convoluted tubule actually comes back around and makes contact with its own afferent and efferent arteriole. So these would be the macula densa cells, and then this would be the JG cells. So when you're looking at absorption in the kidneys, the your ions, as they're filtered through here, whatever the osmolarity is in here will be the same osmolarity here, since it's non-selective for that. So let's say that our osmolarity was at 296 milliosmoles. Well, it's going to be at 296 milliosmoles here. Now, the ion that contributes most to that, of course, is sodium. So if I'm at 140 milliequivalents per liter of sodium here, I'm going to be at 140 milliequivalents per liter here. Now, the vast majority of your sodium is going to be reabsorbed in this area. So you're absorbing about 67 to 70%. And so a lot of it is being taken in this way, is I'm bringing sodium into the cell and I'm kicking hydrogen ion out of the cell. And so there's that antiport. But another way that sodium is brought into the cell is through secondary active transport with glucose. So if my glucose was, let's say, 95 milligrams per deciliter here, it's going to be 95 milligrams per deciliter here. But by the time that I get to the end of the PCT, almost all my glucose is being reabsorbed. And the reason for that is these symporters. Because what's going to happen is, as glucose comes along, sodium first is going to bind to this symporter, and this is called an SGLT, sodium glucose transporter. Sodium binds, which changes the binding affinity for glucose. Glucose binds, and then it kicks the sodium inside, and then glucose goes inside. It drops. When sodium drops off, it changes the binding affinity for glucose. Glucose drops off. Now my sodium is inside the cell, and my glucose is inside the cell. Now, as you can imagine, if I'm reabsorbing about 67 to 70% of my sodium here, that means that as it's coming in on the apical surface, I need to be getting rid of it on the basolateral surface. So on the basolateral surface, what I've got is I've got strong activation of these sodium-potassium ATPase pumps. And so what's happening is sodium is being driven out of the cell through the activity of these pumps into the interstitium, and then it's going to diffuse back into blood for reabsorption. And then at the same time, I'm bringing from the interstitium, I'm bringing potassium into the cell. Now, this part of the kidney counts for quite a bit of our basal metabolic rate. In fact, 6% of your basal metabolic rate is because of these processes in the kidney, and a lot of it is seen in this area, but also in the ascending loop of Henle. What's interesting is because I have such strong activation of these pumps, I'm really extracting a lot of oxygen. So if we look at arterial blood coming in to the kidney, let's say my SaO2 is at 100 and my PaO2 is at 100. By the time I get into here, my PO2 is about 50 to 60. So here it's about 50 to 60, that's your PO2, and that would make your SaO2, that would make it about 85 to 90%, all right? Now, by the time I get down here, I've extracted so much oxygen that by the time I'm down here in the medulla, the PO2 is going to be anywhere from about 10 to 20. So let's say it's at 20. Well, that would make my SaO2 at about 35%. So you can see I've really extracted a lot of oxygen, and that's because of all these active transport pumps that I'm running. So for example, as I come up on the ascending loop of Henle, what I'm doing is I've got cells, and these tubule cells have these pumps, and these are we've referenced them before. They're a sodium, potassium, 2 chloride ion pump. And it's being pumped into here, into the interstitium, and then I'm increasing my sodium chloride within the interstitium. Now, what that does is that allows water to be drawn out on this side and then go back into the peritubular capillaries. And so what I see is I see this change in filtrate as I move along. So I start over here at 296 milliosmoles. I'm at 296 milliosmoles in here. But now what I'm going to do is I'm going to start pumping out sodium and glucose. And then as I come down this way, what I'll see is this will increase. Now, if these are juxtamedullary nephrons, you're going to see this number increase to about 1,200. So the osmolarity in here is about 1,200. Now, the reason for that is because I remove the water, because the water is moving out all along here. I'm pulling H2O into the interstitium. Now, as I come up this direction, what I'm going to do is I'm going to start to remove the solutes on these sodium-potassium 2-chloride ion pumps. And this is strong, strong activation. Now, since these don't have aquaporins in their apical surface, water can't follow. And so what I'll see is I'll see this diluted down to about 100 milliosmoles in the late DCT and then the cortical collecting duct. So just to summarize what happened over here is I started off, if I just took a sample of your filtrate here, I had water and I had solutes in it, and it was about 296. By the time I went down here, what I'd done is I had removed a lot of those solutes, and so the water level dropped and I concentrated the solutes because I'm pulling water out here. Well, the driver for pulling water out here is the sodium, potassium, and chloride I'm pulling in off this side. So by the time I get over here, so I went from 296 to 1,200, and I really concentrated those ions by pulling the water out here. But now as it comes along this way, I've slowed the filtrate because I've pulled the water out. And so now I have lots of solutes that are coming in contact with these sodium, potassium, 2-chloride pumps. And so now what I've done is I've removed the solutes, and I'm down to 100 milliosmoles in the late DCT. Another thing that we showed you before is that if I were to block this pump, what's going to happen is I'm not going to pull water out on this side, and you're just going to end up diuresing all that. And so furosemide is your strong diuretic because you're not allowed to pull that, you're not pulling that water out. Okay, so now I want to look at the normal physiology here first, and we're going to show you what happens with the drop in volume. So under normal circumstances, this is what's taking place. I'm pumping all these ions back in, and here I have a high need for oxygen because I need to run these ATPase pumps, and so I need to maintain oxidative metabolism in order to get that 36 ATP. Now, under normal circumstances, if I flip back over here and I'm at 100 milliosmoles, that means that my sodium chloride in here is approximately 100 milliosmoles. Now, on here, I've got the ability for sodium chloride to leak into the macula densa cells. In response to sodium chloride entering the macula densa cells will release adenosine and ATP. Adenosine and ATP will then plug into receptors, these adenosine ATP receptors, on the JG cells. Now, when adenosine and ATP plug into receptors on JG cells, what it does is it actually will open these little calcium channels, and calcium will come in, and of course calcium will cause vasoconstriction. So these are considered a vasoconstrictor paracrine, and these vasoconstrictor paracrines are always continuously released. And that way I can change regulation of the JG cells. So let's say now what we're going to do is we are going to drop your perfusion pressures. So let's say my mean arterial pressure is dropping, I'm dropping the perfusion pressure. So let's just walk through what's going to take place. As I drop my perfusion pressures, I'm still going to have the same osmolality of filtrate, but now I'm moving stuff through slower. And as stuff moves through slower, I end up actually pumping out more solute. So the lower my GFR, the lower my net filtration pressures, the more solutes I'll pull out. So now I come around over here and I've pumped actually too much out of here. So now I'm less than 100 milliosmoles. Now let's look what happens. If I'm less than 100 milliosmoles, that decreases the sodium chloride that's entering into the macula densa cells. If I decrease the sodium chloride entering into the macula densa cells, I decrease the adenosine and ATP released from the macula densa cells onto my JG cells. What that's going to do is that's no longer going to hold open that calcium channel, and calcium cannot any longer come in, which causes them to relax, which will increase my net filtration pressure. But the other thing that happens is it stimulates the JG cells to release renin. All right. Now, the JG cells, even before I got to that point, had already released renin. And the reason that they were releasing renin is because when I dropped my perfusion pressures, these mechanically gated calcium channels also started to close. And so as the chemically gated calcium channels started to close, there was less suppression of renin release, and I started to increase renin. So renin release is mediated by the mechanoreceptors, which are the JG cells. Again, a decrease in pressure. If I decrease the hydrostatic pressure of this capillary or this arterial, it's going to close down those calcium channels and release renin. At the same time, if I slow my filtrate through here because my perfusion pressures have dropped, I'm going to pump out more sodium chloride. By the time I get over here, I will have a lower osmolality, and now less sodium chloride's coming in, and that will also stimulate the JG cells to release renin. And so we'll just quickly review what renin does. Renin is going to convert angiotensinogen into angiotensin 1. Angiotensin 1 is then going to be cleaved by angiotensin-converting enzyme, your kinase 2 enzyme, into angiotensin 2. Angiotensin 2 will actually try to increase the blood pressure in here by increasing your glomerular hydrostatic pressures. So angiotensin 2, and by the way, the endothelial cells release kinase 2. So I have AT1 receptors on the efferent JG cells, and it'll cause vasoconstriction of those cells to try to bump my pressures back up. But the other thing that renin's going to do is the angiotensin 2 is going to do is angiotensin 2 is going to plug into AT1 receptors on the zona glomerulosus, which gives me aldosterone. And so I've stimulated the synthesis of my mineralocorticoid aldosterone. All right, and then the other thing it's going to do is plug into V1 receptors, AT1 receptors on the paraventricular nuclei and the supraoptic nuclei in the hypothalamus, and I'm going to release ADH. So when aldosterone comes over to the principal cell, aldosterone is a steroid hormone that's going to go right into the cell, plug into a mineralocorticoid receptor. It's going to open a gene site in the nucleus. That gene site is going to code for a sodium leak channel, and it's going to code for a potassium leak channel. So now I can bring sodium in, and potassium will leak out. I'm going to code for a sodium-potassium ATPase pump. So I'm going to pump my sodium back out here. So I'm going to increase the sodium in the extracellular fluid, and then I'm driving in my potassium from outside the cell. And then the other thing aldosterone does is it acts as a second messenger to actually strongly activate these pumps. And so the problem started because I had a drop in pressure. Now what I'm doing is I'm increasing the sodium reabsorption because sodium pulls water, and that's where my ADH comes in. Because ADH is going to plug into V2 receptors, which then activates these little vesicles of aqua 2 porons to insert themselves into the apical surface. Now I have a means by which to get water back in here also. So I'm increasing my sodium, increasing my H2O. That leads to an increase in blood volume, and that should lead to an increase in perfusion pressure. So that's how the kidney protects itself and maintains these perfusion pressures. So on the next video, we're going to show you what happens with acute kidney injury, and then also how it sets up acute tubular necrosis.